Hi there, I'm Dario Cazzola from University of Bath, and today I'm presenting a new method that we developed to estimate the neck muscle activation during pre-input events. To do so, we use rugby as a case study, given the content nature of the sport, but also because from a sport biomechanics perspective, we are now able to reliably measure the kinematics and kinetics of activities like tackling, as you can see in this video, or scrummaging. In the literature, there's been few attempts in relation to the estimation of neck muscle activation or forces, but mostly these kind of tests were very much controlled tests in the lab, as you can see here on the right-hand side, or from a neck muscle activation perspective, fine wire EMG was used, and that, of course, can be used only in a very controlled environment. However, if you think about our application, and that's a video from one of the tests we run, this is rather non-controlled and quite dynamic, and therefore the same kind of approach cannot be used. Therefore, the aims of this study are, first of all, to develop and use a new EMG-assisted neuromuscular skeletal model to estimate such neck muscle activation during dynamic events or collisions. And the second one was to identify what the level of subject specificity needed to do so to reproduce really the data that we collect, in this case, neck joint moments and muscle activations. The method used included in vivo experimental methods, which included a full body MRI scan of a single semi-professional rugby player. As you saw before, we collected kinematics and kinetics during both scrummaging here and tackling. And also we collected EMG from 4 different muscle groups. 2 EMG was placed close to the sternocleidomastoid, and the other 2 EMG were placed close to the trapezium, as you see in the figures there. In terms of computational methods, we mainly firstly developed a new musculoskeletal model. As you can see here, this model is informed by the use of MRI scans that were used to create rapid surfaces and inform the mass distribution of the model itself. Once the model was created, then we moved towards the development of the modeling framework, which included 2 main blocks. The first one here is based on the use of OpenSim libraries and procedures like inverse kinematics to calculate the intervertebral joint angles, inverse dynamics to calculate the net joint moment of the cervical spine, and muscle analysis to calculate the moment arms and the muscle tender units, lengths, and velocities. The second block here was mainly based on the use of CineMS, which is an optimization algorithm that allows to run a calibration, so calibrate the muscle parameters of the model, and solve the redundancy problem in different ways. In our case, we solved them, which means essentially we calculated the net muscle activation in 2 different ways. Using a static optimization approach, where essentially the muscle activations are estimated using a priori function, which in this case was a minimization of the square activations. While the EMG-assisted approach is mainly based on tracking some experimental data, in this case EMGs. And what we've done here, we try to use EMG-assisted approach in 2 different ways. One is called EMG-assisted, EMG-A, and the other one is called EMG-assisted MRI. The main difference between the 2 approaches is that the EMG-A MRI is informed by parameters coming from the MRI scan that will be collected. In the next slide, I'm going to show you what are the main kind of metrics that we use to evaluate the 3 methods. And the first metric I'm showing you is the tracking of the net joint moments. As you can see here, I started with the flexion extension, and the set of graphs that you see here are essentially showing how individual net joint moments across all the kind of activities and trials that we had are performing in terms of root mean square error, and R squared. Here below you can see is a distribution of the data and how the EMG-assisted and EMG-assisted MRI are performing with respect to the static optimization. The same thing was done for the lateral bending, and I summarize here for you the positive, green, neutral, amber, and kind of negative results that we can find here. So surely we can say that in terms of net joint moment tracking, which usually static op is very good at, we can see that for flexion extension, our EMG-assisted approaches do very well, both in terms of RMS error and R squared values. For the lateral bending, there is a less positive kind of picture there, but again, the EMG-assisted MRI is very close to static optimization in terms of RMS E and R squared. If we move towards the second metric, which is the tracking of the actual EMG signals that we measure, so the experimental data, we can see that clearly the EMG-assisted approaches are outperforming the static optimization, with statistical differences both in terms of the RMS E and the R squared here, with very high R squared with respect to the static optimization. Finally, the last method that we use is the co-construction index that was calculated for both the flexor and extensor here and the lateral bending muscles, so divided by muscle groups here. And that's done for the static optimization and the other two EMG-assisted methods. To give more context, this kind of index should be equal to 0 when you got full co-activation in between antagonist muscles. In this case, what you can see in black solid lines are the experimental data, whilst in the blue, amber, and green, you can see the same kind of co-contraction coefficient index for the different methods. And it's clear visually that if you use an EMG-assisted approach, either the first one here or the one informed by MRI, the co-contraction index is much closer to the experimental one, which is a very important thing, especially when you're dealing with pre-impact events, because it means that you're really capturing the co-contractions that are happening there, and therefore you are more likely to calculate the right internal load or joint reaction forces. To conclude, I would like to underline that EMG-assisted modeling should be the way forward when you want to estimate neck or spinal muscle activation, especially during impact events. And there are 4 main reasons why we believe so. The first one is related to the very good net joint moment estimation across the entire cervical spine. Most importantly, the ability to replicate experimental co-contraction in the estimated activation. Then using EMG-assisted approaches, you are not using any a priori objective function. And 4, we're also showing that more detailed MSK modeling could really improve your estimation. Thanks for your attention.